And once again, good morning, everyone.
Good morning, sir.
I want to look at the quiz I sent to you. Unfortunately, about 75% of the class didn't do it. I wonder why. I sent it some.
Good morning, sir.
Yeah, good morning. I sent it some 2 days ago.
Yeah, actually, so most people are actually busy in one place or the other. I guess it was this morning. Most people plan to do the test. Actually, the work has been so hectic here on all sides. So we are sorry, but they will still attempt later.
There is no need attempting it any longer because
Okay, we are doing correction now.
Yeah, the
Okay, sir.
The purpose for it has been defeated already. Well, in any case, we should find time to do so many of these things. It wouldn't take more than 1 hour. If we had planned to do it, I believe we would have done it. So let's quickly go through. It would have just solved a lot of issues here. Just the kind of revision, so to say. Well, an alpha particle consists of, can you see the screen I'm sharing? Hello?
Hello, sir. We can see that alpha particle. I can see a screen that shows from timer or something.
Timer. Okay. Yes, okay. Sorry. Okay. You should see that now.
Yes, I show you now.
Okay. Well, let's see how we can crisscross through all the questions in less than 1.5 hours. An alpha particle consists of blah blah blah. You should know that. An alpha particle consists of what should be the answer? It shouldn't take us time.
2 neutrons, 2 protons.
Yeah, 2 neutrons, 2 protons. So 2 elements with the same Z but different A are called what?
Isotopes.
Okay, that's
isotopes.
Straight. Yeah, that's straight actually. So what is the following? Which of the following is true? Which is true? ABCD.
I think the answer is D.
D is correct.
Yeah, because isotopes, they have the same number of protons, which implies that they also have the same number of electrons. So D is straight of the answer. The questions we have these days should be something simple. Oh, I think I have made a mistake. Okay, let me see if I can do something to it. We'll see. Okay. Okay. Number 4. The binding energy of an atom is dash. What's it? Well, so the answer I mistakenly pressed is the energy required to remove an electron. Yeah. It's shown already. 5. Let's see this. The energy levels, K element of Thomson and blah blah blah. What photon energy should be present in this characteristic spectrum?
A.
How? How is it A?
Well, for K alpha characteristics X-ray, that will be from the adjacent cells, the K and L cell, which is 69.5 minus 11. That gives us a 58.5. Then from the M to K, that is 69.5 minus 2.5. That gave us 67. Then from M to L, that gave us 11 minus 2.5, giving 8.5.
Okay, that is it anyway. But the order of subtraction should have been this, the bigger minus the, this is the bigger energy. This should be 11 minus this, this minus 2.5 minus this there minus 2.5 minus blah blah blah. But in any case, we still have the same answer. Just for us to know that this is the highest energy, the energy of the this has the highest energy, M shell electron, the outermost, followed by the innermost, which has the least energy, but yet is the one with the strongest and binding energy. In any case, that's correct. A, subtract from one shell to the other. I mean, do the difference of the energies in the two shells under discussion, the two shells concerned. 6, which of the following is not an electromagnetic? Okay, one is a bonus.
E.
E. Wow, I thought it should be a bonus. E.
B.
Okay, somebody said E. Why E? Why B? It's just for us to know.
Sound is an example of mechanical wave.
B is the answer.
Okay, someone said E. Why is it not E? Or why is it E?
I think the person said B, sir, not E, sir.
Okay. Well, in any case, why is it not E? Substantiate your claim that it is not E.
Anyway, the reason why I picked ultrasound was that I know ultrasound is more of a mechanical waves.
Yeah.
It's not a electromagnetic waves. So the heat radiation, well, I just well, it cannot be more than one answer on this one. That's why I don't know the reason why it's not heat radiation actually.
So that is why multiple choice, one shouldn't have problems getting over some of these multiple choice questions because the best answer. If it had been a case of a true false, I think we might have come into some problems when we get to it. It's actually infrared ray. The form of electromagnetic radiation given off by heat is an infrared ray. Infrared radiation, and infrared is of course a part of the electromagnetic spectrum. So whenever we see heat ray, of course we should know that it is one of the components of electromagnetic radiation, infrared. You should always know that. So in 7, 400 keV photon, the dominant mechanism of ionization in muscle tissue is what? Why photoelectric? Why coherent scatter? Why is it photoelectric?
I think I missed this. I picked photoelectric, but I'm just thinking maybe it could be something actually.
Why? We should have some informed discussion on this. Inform them answers. If we are choosing an answer, why are we going for that? Because okay.
I think the answer is Compton, sir. Because in Compton's in photoelectric, okay, sir. In photoelectric, we need a low energy, and at the same time a low atomic number for photoelectric to actually happen. But in Compton, as the energy is increasing, then Compton dominates.
So in addition, sir, the element that make up most of the soft tissues are low atomic number elements like carbon, nitrogen, oxygen, and nitrogen, which are more in the soft tissues. So with this energy range, 100 kV volts, most of the photons we actually, I think, will give more of Compton because there will be scattered photons because they won't be able to absorb most of those and the energy photon at this range. That's my own addition, sir.
Okay, we are playing around the answer. It's okay, it's Compton, but they will absorb the energy. The tissue will absorb. It is when the tissue absorbs this energy, then so many things begin to happen. Coherent scatter, electric, and the compton, they all begin to happen at this energy. But for 100 keV, coherent scatter is almost zero. It's almost zero. And the major ones will be left with electric and the compton. But for soft tissue, at this energy, the major mechanism is a compton. Yes, a question that will give us a better clue. That is, there's a particular energy in soft tissue when these two energy, a particular energy when these two processes, that is compton and the photoelectric, they become equal. They become equal at, of course, so many variables. The major variables are the type of a tissue involved, that is the effective zero from that tissue involved. But for soft tissue, we have a particular range. So we get to that question later. So for 100 keV, it's essentially compton contributes more than 50% of the interaction. Number 8, photoelectric. Quickly do that. We have less than about 10 minutes to go.
Hello, sir. Can I quickly ask the questions on the previous questions, sir?
Okay.
Yes, sir. So let's assume that
Hi. Hello. Hello.
Hello, sir. Can you hear me, sir?
Okay, I can now.
Okay, I said the previous question, sir.
Yes.
Assuming it's not just soft tissues, maybe ionic contrast was added to the soft tissues. Will this still be compton or photoelectric, sir? Thank you, sir.
Okay. If you add iodine to the stuff, compton will still be there, but because of the K edge, the elevation of the photoelectric effect by the K edge energy of iodine, we're talking around the 33. So there's something will now shoot up. The photoelectric effect and contribution will now shoot up because so many so many of the atoms there will now be available to undergo photoelectric emission. So photoelectric emission will now be greatly enhanced. Then the degree to which it becomes enhanced now depends on so many things, which you might not readily see. But what we do know is that the photoelectric effect will be seriously increased. Maybe initially, if the contrasts were not added, we might have maybe 80-20 for compton. Then if you now add the photoelectric, the compton, and the iodinated contrast, you might now have the photoelectric effect going up to maybe 50, 60 as the case may be. It all depends on so many things. And of course, the energy of that, the energy involved with that would be the photon energy will not be around them 100, around them 30 or so. And we are looking at 100 keV photon. For 100 keV, assuming it is a mono-energetic 100 keV photon, then there wouldn't be any photoelectric effect will not increase because we wouldn't be able to have that K-edge contribution, that is K-edge advancement or the improvement of a photoelectric effect due to K-edge. But since we are using polyenergetic beam, that is when it will have an effect. The photoelectric effect will have an effect because it just because this beam is polyenergetic from 2030. Most of the beam coming in with 30 will now enhance the photoelectric effect. Whereas, of course, a compton will still continue to take place. So if it is a monoenergetic photon, then compton effect will continue. Photoelectric effect will just remain at the level it was before. Bringing in contrast will never have any advantage whatsoever. or because we are dealing with a polyenergetic beam, of course, and so the iodine contrast will then have an issue there by increasing the photoelectric effect. So 8. I hope I made some little sense.
Yes, sir. Thank you, sir. It's very clear, sir. Thank you, sir.
Okay, 8.
B.
Photoelectric effect occurs when an atom is ionized by B.
I think B, sir.
B. Theta ray. Okay. Well, that's wrong. Both for is either gamma ray or X-ray. It is neither alpha ray nor beta ray. I'm talking about interaction of radiation. The radiation we are talking about here is the gamma rays and the X-rays. A beta ray is another level. The interaction of a beta ray will lead to subsequent types of a reaction. Of course, if the beta ray is coming, because we are talking about the electron interacting with maybe orbital electron, because what happens is characteristic emission or other electron emission and so on. So it is gamma ray that will interact with it and give its energy to the electron there, maybe innermost electron or outermost electron, as case may be, for photoelectric effect and so on and so forth, and so many other things that we need to have. So gamma ray, they ionize the atom via what's it called, via photoelectric effect, and then a Compton effect, Compton scattering. So it is actually gamma ray.
Okay, sir.
Incoherent or Rayleigh scattering, and the energy of this photon is dash.
D, option D.
Yeah, left unchanged, nothing happens, continues. So to say, it's left unchanged. But this is a conservative notion. It can never be left unchanged. If there will be a little change in reduction in energy. But any case, that's shouldn't bother ourselves. For now, let's just take it. It's left unchanged. Concerning pair production, which of the following is true? You don't have a problem with this.
I think option B, sir.
Option B.
I pick B. B, yes, sir.
Concerning pair production, an electron and a position are produced. Straight up, that's the answer.
Sir.
Yeah?
No, I pick option B, but this option D, what they mean by the annihilation produces 1.02 megaeV photons?
Annihilation has got to do with the positron that has been produced in pair production. The positron that has been produced in the electron will continue on its own path, continue doing some crazy things, maybe interaction with the electron, with the nucleus, and so on and so forth. Whereas the positron will also want to undergo its reaction or an interaction with that in that volume of tissue or whatever the place it's been produced. But because of the nature of a positron, it just immediately interacts with the electron. Maybe free electron in the shell, in the tissue, in the atom or whatever, or bound electron. So immediately its journey ends almost as it is produced. So when it is produced, it now comes together with, it combines with the electron to be annihilated. So during that annihilation, we have a production of a gamma ray, which has an energy of 1.02 megaelectron volt, at least. Did you get the logic there?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
So 11, if radiation is not electromagnetic, I don't think we have any mistake.
Hey,
Ultrasound. 12, X-ray photons and gamma always define what?
they find their origin.
Yeah, why not energy? How do they differ in their origin?
Well, the gamma rays are mostly they are produced from the nucleus. They are nuclear particle from the nucleus, nuclear transition. While the X-ray photons are more of a well, it could be a breaking radiation, which is more of interaction of the incident electrons being deflected by the Coulombic force of the nucleus, or directly with an orbital by characteristic X-ray production. So it's more of a electronic stuff. Why the gamma rays from the nucleus?
Okay, well, for me, the question is not too straightforward because X-ray photons can either be from the orbital electron, interaction of electrons with orbital electrons, or interaction of electrons with the nucleus. In the nucleus, we have the Bremsstrahlung X-ray, and whereas the one from the orbital interactions constitute a characteristic S-ray. But be that as it may, it is the answer is still D, because gamma ray is essentially with producing the nucleus, whereas X-ray. The X-ray here, I want to believe, is the characteristic X-ray, which of course is originates from interactions of electron with the orbital. I mean, with the orbital electron. So is D is the best answer. So they can also have A can also be an answer, but not the best, because gamma ray they are much more energetic than X-ray photons, because a gamma ray as a result of the transition between the nuclear subshells, which have much more energy. They have the nuclear energy there, the nuclear force binding them is characterized by strong force. It's one of the characteristics of forces in nature, strong forces. So the transition between, like we have an electronic transition from one shell to another, giving up to a characteristic. So we also have that in the nucleus, from one nuclear shell to another nuclear shell. Transition there, the transitions there are what give rise to gamma rays. So because you can see from L to K, you might have just around 100 keV, but from L to K in the nucleus will result in a monumental amount of energy. So it's essentially D. Though if we have to choose another one that is closely, then we have to go for the energy. Isotopes have nuclei. This one shouldn't have this time. Number 13.
B.
B, they have the same Z. 20. Number 14. The number of neutrons is just 60
C.
minus 27 is C. 15. The number of nucleon per is what?
D.
D. Some of the neutrons and protons. That's the nucleons, the nuclear particles, which is the mass number. The binding energy of an electron in the K shell is
D.
the energy to remove electron from the K shell, yeah?
D.
Yeah.
D.
17. The mass number of an atom is equal to
C.
Yeah, nucleons. That's proton and the neutron. That's the nucleon. Electron binding energy. Yeah. So electron binding energy.
B. Option B.
Option B.
Yes.
It's greater for the K shell of barium than
Yes.
the K shell of hydrogen. Why? How?
Yes, because electron binding energy is atom dependent. As with increasing atomic number, it also increases because the Coulombic force of attractions increases as the number of protons increase, which also increases with atomic number. So
Yeah,
with
no,
the increased atomic number, leads to
yeah,
more increase.
yeah, no contest from there. That's straight. 18. Okay, 19.
Okay, LB.
B, L.
B.
C, M. Another one, D, N. I have to be careful here. It is actually K. K is the closest. Okay, second closest. Sorry. That's L. Sorry.
Yes. Sir.
Yeah. Sorry.
Yes. Sir.
K is the closest to the nucleus, followed by L, M. That's the order that has been conventionally agreed. Nucleus with the same A and different Z are called what?
Isobars.
Yeah, isobars.
Isobars.
Yeah, the A there.
E.
Isobars.
Cobalt 58 and 57
Yeah,
have,
B, sir.
yeah, same. B, same atomic. Come again. B,
Same, that is 21. I same atomic number.
which is what?
Then that 21 is A.
I thought you said the same atomic. B as atomic number. Yeah, the same atomic number. That's an A.
No,
The
no.
same,
A is correct answer.
yeah, that's atomic
The
number.
same
They have
number
this,
of orbital electrons.
yeah, which is also the same number of atomic number, the same atomic number. Hmm? Are you with me?
Yes, sir.
Yes, sir.
Yeah. The cobalt
Yes,
57
sir.
and 58, they have the same atomic number. That is why they have the same orbital electrons. "22. Which is not true regarding electron binding energy.
A.
A is equal to the energy of K of a K characteristic. Well, that one doesn't make sense. It doesn't make sense. So A, but for purpose of understanding it, greater in K share and L share, yes, increases for given share with increasing atomic number, yes. For L, it's less than that of, yeah, still the same thing. Okay, 23. Oh my God. Something happened here. Anyway, in any case, we are still okay.
I think it's back now.
Let me get the question. Characteristic X-ray are so known because they are characterized by, let's go to the options. Okay. They are characterized by,
B.
yeah, the electron binding energy. They
Option,
have them. Are you, is that the final answer? Is that our final answer?
Option
yes,
B.
B, option B.
Okay. Okay. Let's hope so. It's actually B. Okay, let's have this. Thomson has the following binary registers indicated in the table below. In order to observe 7 keV characteristic, the incident energy of the electron must have what? What's the least energy the electron must have?
B, 70.
Why is it 70?
Because we are talking of characteristic X-ray. And for it to occur, the incident photons must have an electron greater than photons greater than the binding energy of that K shell. For the K shell here, the energy is 69, and the one that is closer to it is at least 70. 70 is higher than it.
Well, they said 57 keV. We want to look at 57 keV. So how does your explanation now, how does it justify?
Yes, because if the incident energy removed the electron from the K shell, which have an energy of 69, and another, I think from there's movement from L, another electron fill it from L to K, which is 69 minus 12. That should give us the 57K characteristic X-ray that we produce. So, but the energy required to remove that electron from the K shell must be greater than 69, and that's why I go for I pick 70.
Okay. Yes,
Hello, sir.
Yeah, I can hear you. 69.
Okay.
12, 2, 1. Okay. Let's